All right, let's talk shop. If you're in our world, HVAC energy management, you know that everything we do boils down to physics and finance. This isn't a beginner's guide. This is a deep dive, from one pro to another, into the mathematical toolkit we rely on. These are the core equations that really separate the experts, the tools we use to analyze, optimize, and justify every single move we make. So, here's the game plan. We'll kick things off with the language of efficiency, then jump into the physics of fluid dynamics and heat flow. After that, we'll get into the weeds of advanced chiller modeling, and finally, tie it all back to how we actually manage these projects.
First things first, let's talk about the core metrics. These are the numbers that let us benchmark equipment and really start building the business case for any efficiency project.
And we have to start with the most universal metric of them all, the coefficient of performance, or COP. It's just a pure, simple ratio. It tells you exactly how much heating or cooling you get for every single unit of energy you put in. For a chiller, that's the heat you're pulling from the evaporator divided by the compressor's work. For a heat pump, it's the heat you're delivering. It's our absolute baseline for thermodynamic efficiency. Higher COP, better performance. Simple as that.
Okay, now for a classic one, EER versus SEER. This really comes down to the lab versus the real world, doesn't it? EER is that perfect snapshot at one specific design point. It's great for figuring out your peak load performance. But SEER, well, that's what gives you the practical, season-long picture. It factors in part load performance, which, let's be honest, is a much better predictor of what your annual energy costs are actually going to be.
And this is where the rubber meets the road. You have to be fluent in these conversions. Being able to jump between spec sheets means knowing this stuff cold. That 3.412, that's just our magic number to get from a pure COP ratio to BTU per watt hour. And knowing how to quickly flip between EER or COP and kilowatts per ton, well, that's just a fundamental skill for doing quick comparisons on the fly.
All right, so we've got our static ratings down. But the real money, as we all know, is in the dynamics. It's in the moving parts. Let's talk fluid dynamics. This is where the biggest savings are often hiding.
Okay, if there is one equation you absolutely have to have in your back pocket, it is this one. The Affinity Law for power. It's so powerful. It tells us that the power draw of a fan or a pump is proportional to the cube of its speed. It's not linear. It is an exponential relationship, and that changes everything. It's literally the entire reason VSDs are such a game changer.
The variables here are super straightforward. You've got your before state, your initial power and speed, and your after state. That's it. It's a simple relationship with a huge, huge impact. Again, it all comes back to that little exponent of 3. Think about it. Flow is linear with speed. Pressure goes up with the square of the speed. But power? Power takes this incredible cubic leap. And that is precisely why a VSD isn't just a small tweak, it is a fundamental shift in how we manage energy in our systems. So let's make this real. Look at this number. How do we get there? Well, say you back off a fan speed by just 20%. So you're running at 80%, or 0.8 of the original. Now do the math. 0.8 cubed is about 0.512. That means you're now using just over half the original power. That is a 49% cut in energy for a modest 20% reduction in speed. It is absolutely incredible when you see it in practice. Okay, so we've nailed the equipment efficiency and the fluid dynamics. But what are those systems actually doing? They're moving heat. So now let's talk about how we quantify the load itself. The old reliable, the sensible heat equation. This is our bread and butter, isn't it? And that constant, 1.08, we all use it every day, but it's good to remember where it comes from. It's just a neat package of standard air's density and specific heat times 60 minutes. It just makes calculating the energy to change air temp so much easier.
But as we all know, especially in humid climates, temperature is only part of the puzzle. You have to account for the moisture, the latent load, and that's where enthalpy, our good friend delta H, comes in. This equation gives you the total heat picture. And that 4.5 constant, same deal as before. It's just a helpful shortcut. If you're not using this equation, you're flying blind on your dehumidification loads, period.
Now, of course, we all get the distinction here. That's day one stuff. But where the real pros stand out is in not getting tripped up by it in the application. How many times have you seen a system designed on sensible load alone? It leads to undersized coils, comfort problems, the whole shebang. Getting this right is absolutely non-negotiable for a high-performing system.
Nameplate data is fine for our first pass, but if you're serious about optimizing a central plant, you have to go way beyond static ratings. We need models that can predict how these things actually behave out in the wild.
This is the million-dollar question, isn't it? How do you model a machine whose efficiency is all over the map, depending on its load, the condenser water temp, on everything? A single kilowatt per ton value just doesn't cut it. It's a moving target, and we need the right math to track it.
Well, we do it by using a progression of models. You can start simple, but as you add more layers of complexity, like bringing in the actual condenser and evaporator temperatures, you get closer and closer to reality. And at the very top of that pyramid, you have the most robust tool we've got, the Tri-Quadratic model.
And here it is, the big one. Now, it's important to remember what this is. It's not a first principles physics equation. It's a very sophisticated curve-fitting model. You feed it a ton of real performance data, and it spits out these coefficients, A, B, C, and so on. And look at all those terms. It's not just looking at load and temps, it's looking at how they interact with each other. This is the secret sauce inside the best energy modeling software. It's how we get truly accurate predictions.
Okay, for our final section, let's bring it all home. We've gone through a lot of math, but let's be clear, this isn't just some academic exercise. These are the tools we use to drive the real work, day in and day out.
Just think about our workflow. During an audit, you're using the thermal load and performance equations to find opportunities. When you're building the business case for a VSD, you're whipping out the Affinity Laws to quantify that ROI. And at the end, for M&V, you're using those exact same equations to prove you delivered the savings. Every single step is built on this mathematical foundation.
But let's be real for a second. We can build the most elegant, beautiful models in the world, but they are only as good as the system is operated. All it takes is one manual override or one piece of deferred maintenance, and our perfect calculations can go right out the window. The human element, that is always the biggest wild card in all of our equations, isn't it?
So, what this all really comes down to is that this toolkit is our universal translator. It's how we take the physical reality of our systems, the airflow, the temperatures, the motor speeds, and turn it into the language of the boardroom, operational costs, capital investment, and return on investment. That's our real job, bridging that gap.
So I'll leave you with this question. You have the toolkit. We've just walked through it. So where's your next big win hiding? Is it applying the Affinity Laws to an overlooked pump? Is it diving deep into a chiller model to perfect your plant sequencing? The opportunity's out there. It's just waiting to be quantified. Thanks for diving into this with me.